So it deforms and it doesn't spring back into its original shape. So those are useful when you're considering safety factor. Now, one of the most important things about vacuum chamber design is to make sure that it's actually a vacuum. And for that, you need to put in O-rings at the top and the bottom. So the vacuum chamber, it has three pieces. I guess I didn't say this explicitly before. You have the ring-shaped piece here, and then a bottom lid, and then a top lid that's not shown in this picture. Pattern of bolt holes, O-ring groove on either side of the body plate. And also Teflon tape here to seal the port feed-throughs to the body. These aren't welded, though it's possible if you have access to a TIG welder, you could weld those pieces on. Now, in a bit more detail about the port feed-throughs, so you want to use tapped holes, ideally with an NPT threading. That's just one threading specification that's especially good for low-pressure applications. And just wrap Teflon tape about it. On the website, I go into more detail about this. And then that holds up to 10 to the minus 3 torr, very low. And you want to use rubber O-rings, Viton or Buna N, for the gland design. There's also a very good website on gland design. I give that URL there. And that just shows things like, well, if I have an O-ring of this diameter with this cross-section, I want to make the width of the gland this much, the depth this much. So it's straightforward. Also, a brief aside on the type of O-rings you should use. Rubber O-rings, yes. Teflon O-rings, you don't want to use those. Those are for like rotating applications, so. Okay, so that was the end of the vacuum chamber design section. Now, going into the RF system, here's just an overview of that there. Here, top view of the cyclotron body with one of the electrodes, and then feeding into the RF box. There'll be a more detailed picture of that in a few slides. So the way, do I have another picture of that? Okay. So the way this works, you saw in some of the earlier slides that there were two D-shaped electrodes where one of them would be at a negative voltage while the other would be at a positive voltage, and then they'd flip-flop at the cyclotron frequency. So mine I did slightly differently. So you have one copper D-shaped electrode here, and then the body of the cyclotron, and this would go between a high voltage and a negative voltage, and then the body of the cyclotron, which is connected to this copper plate there, would always be held at system ground. So basically, you have one D-shaped D, and then the other D is the entire rest of the cyclotron system. Now these, the electrodes, this is what I'm calling the electrode right here. You can make them out of copper, which gives you better conduction, fewer eddy currents, or brass, which is easier to machine. If you have access to a water jet, it's easy to water jet out two half-circular shapes and then just braze them onto a strip there, so you have the hollow D-shaped piece. And then just water jet out the rectangular piece as well. Right, so as I said before, the square wave is applied to the D-shaped piece, while the rest of the system is constantly held at ground. Now, impedance matching. All right, so while we were talking about mechanical things, the RF feed-through, which I showed you before, that was the aluminum tube that led out to the box. You need to prevent that piece from arcing because you're applying fairly high voltages to the inside of that piece, the copper rod on the middle, while the aluminum tube on the outside is constantly held at ground. So you want to fill it with something like Delrin, which is a type of plastic, to prevent it from arcing. So you can do that pretty easily just by getting the aluminum piping, press-fitting Delrin inside, and then press-fitting your copper tube, and that'll give you a vacuum-type feed-through, which won't arc. Now, impedance matching is important. The vacuum chamber and electrode system, it acts as a capacitor, which makes sense. So you have something at one voltage, something short distance away from it at another voltage. So it's a capacitor, albeit a big, funny-shaped, spread-out capacitor. Now, you want to, good, that's working. You put the system in parallel with an inductor, and just from basic current analysis, it resonates at a particular frequency, which is given by 1 over 2 pi root LC, where L is your inductor, C is your capacitor. So they're in parallel on the circuit diagram. So for example, well, this is your function generator. This is a variable capacitor that we're getting into later. This is your inductor. This is your system capacitor, and that's ground. Now, you have your signal coming out of your function generator that's at a fixed impedance. It's at 50 ohms because that is what they come at. And you need to match your system to this 50 ohms, or else you'll get reflection and you'll lose a lot of your power. So the way you do this is by adding in the variable capacitor, which allows you to adjust the total system impedance. And the resonant frequency remains unchanged by adding in that capacitor. So an easy way to do this, it's difficult to get inductors that are at the inductance that you need, but it's straightforward to make them. So you take some copper wire. This is just 8-gauge copper wire, I believe. Wrap it around something. I used a broom handle. And once you get a coil of maybe 10, 12, 15 turns, you use a network analyzer to measure the resonant frequency of 2 particular systems. So you take your weird hacked-together pseudo-inductor coil, put that in parallel with a capacitor of a known value, figure out what the resonant frequency is. At that point, since you know the value of the capacitor, now you know the value of your entire inductor. Then you take your entire inductor, put that in parallel with the vacuum copper D-shaped system, check the resonant frequency. That tells you what the capacitance of your vacuum system is. So you have that number, which you'll need later on. Now, what you have to do, you need to, assuming your magnet is at a fixed field strength, you'll need to tune your inductor so it matches your cyclotron frequency that you calculated before from those variables. So you need to tap off of the inductor at a given point to measure that. So basically, you hook your capacitor and that inductor up to your network analyzer, and then, well, with your brazing torch, because that's what you need to attach to something as thick as this reliably, you tap off of the inductor at different points along the coil, so different numbers of turns of the inductor are in your system. Keep moving it and moving it and moving it until your system is at the frequency it needs to be at. Oh, and then you use your variable capacitor to adjust the impedance so it's at 50 ohms, and then you're done. Well, you're almost done, except you need to test for arcing. So a good way to do this is basically you set your function generator to put in pulses of, say, 100 watts at a given frequency, and then you tune up your oscilloscope and you make sure